All right, so I'll send out an email, but it'll probably be like 5 or 5:30. And it's not a mandatory thing. It's like if you want to come and have questions to ask, and we'll probably go through a few problems and stuff like that, then that'll be fun to do. So I'll try to set that up, and I'll send out a Zoom link to everybody. So, okay, so the basic structure of the test, it's going to be some true false like you've seen on your quizzes. There will be no surprises there. Since you've done good on the quizzes and you've looked and studied the quiz material, you'll do really well on that part. It'll include some multiple choice, and then there'll be a series of short answer or essay type questions on it, which will get more into having you, a few of those will actually have you use the questions or use the information you've learned to answer questions. And some of that stuff we'll be going over on Monday, Monday's lecture, which you'll see, and then we'll do it again during the review session. Okay, so that's what we're doing. All right, any other questions, comments, difficulties? This is certainly a different way of trying to teach and learn, I know. So let's see how this goes. All right, so what we're going to kind of do here is give you an example, a real life example of how some of this information that you're learning, hopefully learning, can be used and what it means out there in the real world. And so to do that, we're going to take a trip. We're going to go down to South America, and we're going to focus in on this area called Potosi. The mining district is Sierra Rico. This is one of the oldest mining districts in the New World. Mining actually started there in 1545, and it's been mined almost ever since. And what happened then is that tailings materials from this area has kind of flown downstream along this Rio Pilcomayo river system all the way down into Argentina. And so another picture of this, we saw this map earlier when we were talking about the Amazon. And in that case, the gold and stuff was flowing that way. Here is where Sierra Rico is, and where the Spanish first started mining in South America. And then the flow is that direction. So it's tapping these same ore bodies that exist throughout the Andes. All right, this is a picture of Sierra Rico. The name means essentially rich hill, and there's a reason for that, because at the very top of that hill, here's the first Spanish mine. They were able to find native silver. So this was the richest silver deposit ever discovered. And literally, there was pure silver within the rocks. That's now a national or world historic site, and it's literally honeycombed with thousands of mines that have been mined since 1545. So we've had this continuous mining in this area, but it's changed from silver, and it's gone from silver to tin, and then from tin to lead and zinc, and currently it's primarily a lead zinc deposit. And these are referred to as polymetallic ore deposits. So they're ore deposits that contain a whole variety of different types of minerals. In the past, of course, everything was done by hand, but that really hasn't changed much. So if you go there today, this is what you would find. Almost everything internally in terms of mining operations is still done by hand. And so then the ores are taken out of that. Now this was, at one point, Potosi was one of the most important cities in the world, had a population of about 60,000, even back several centuries ago. And the reason for that is that they were mining so much silver here for Spain that they actually set up their own mint. So they would mint the coins. This one's 1776, but they all go all the way back. And then those coins would be shipped over to Europe, and it actually kind of supported the entire economy of Europe for several centuries. So this was an extremely important area. You can see some of the ore deposits that were there. Now, if you want to get into these mines here, it's quite the experience as you're studying this. One like I said, the miners are doing almost everything by hand. And so if you want to go in and tour and take samples of the ore deposits, you have to bring presents. And so what kind of presents do you bring? Well, anybody have an idea what that is? Dynamite. So you take some fuse, you buy a few sticks of dynamite, you might have some ammonium nitrate. This is Mark Couture in the Spanish department. He was down there with this. And so you buy some of that and you take it in. And those types of presents would go to the head honchos. Those would be the people who are overseeing and coordinating most of the mining activity. But for the ones that are actually doing the work, you bring, anybody have an idea what that is? Cigarettes. So you take cigarettes. Back in here, you can't hardly see it, but in this red bag is coca leaves. And so what the miners do, we're at 14,000 feet plus, and you're back at a mine. So it's a really miserable, difficult job. And so a lot of them will chew coca leaves. It's not the same as cocaine, but it kind of numbs the senses and stuff. And then this stuff is actually ash, type of lime. And so they put coca leaves in and they put lime in and it helps break the coca leaf down. It kind of numbs you. Also helps with altitude sickness and things like that. And so that's one item that you would take for the miners. And then up here is this alcohol, and they use the alcohol for two purposes. One is most of their lamps are not battery driven, kind of modern stuff. They are actually burned the alcohol. It's cheaper. And so they use that in their lamps and they also drink it. So dual purpose. So you can take that stuff. So it's a pretty rough, rigorous job to work in these mines. Kids as young as 12, 14 are working in there. And it's pretty difficult. Okay, so once they get the ore out, what do they do with it? Well, they take it to these processing plants, Henios it's called. And this is one of the first step is they put it in a ball mill. This thing just turns around, it's got stuff in it, and it pulverizes that ore until it gets down to about silt-sized material. So this is really kind of fine material from what it was. Then they put it in this kind of device with a whole bunch of different fluids in it. It's called froth flotation. And what it does is through density, different metals, in this case zinc and lead, will float up to the surface. These are paddle wheels, they'll turn, and you'll kick that stuff off. And eventually, they will produce this stuff, which is a lead concentrate. So that is kind of the final product at this mill where it's really high concentration of lead. And then that stuff will be shipped off, and they'll actually use a smelting process to actually refine it even further into lead and zinc. So this is the process that they're currently using. It's not uncommon mining type technique. All right, so the side effects of this. So here's that facility we were just in. There are a lot of these in the around Sierra Rico. And you can see the effluent from this stuff runs down and goes directly into the river system. This is what it looks like. It's kind of hard to see, I guess, in this photo. But it's this kind of bubbling mass of goo. And you can actually see discoloration of the water up about 150 kilometers downstream. So pretty significant contamination. This stuff has a pH of about 10. So all this thing, the liquids and stuff that they put in it to during that froth flotation gives it a pH of about 10. All right, but then we've taken a couple other pictures here of this area. This is drainage coming directly out of the mine. And then this is some drainage along the margins of the river. It's bright red. What's causing that? Oxidation of?
Iron.
Iron would be one, but let's be more specific.
Pyrite.
Pyrite. So that'd be one. It's iron sulfide, right? And that's giving it the red color. But we have a whole series of actual sulfide minerals in there. We might have galena in there. We're going to have sphalerite. We're going to have cuprite. We're going to have a whole variety of sulfides. But certainly pyrite is a big portion of what's causing this, and so this is acid mine drainage, okay? We're generating acid mine drainage along that area. And in fact, this is some of the sediments here. It's that gray stuff, and I don't know if you can see it very well, but you see the gold-colored flakes in there. All of that stuff's pyrite and other sulfide minerals. So we got a ton of those sulfide minerals that are in this drainage system and being flushed out into the river. Okay, and all that has the potential to be oxidized. And when we do that oxidation, what do we produce? So here's pyrite, iron sulfide, little oxygen, little water, and we get. So what's that again?
Oh, I'm sorry.
Iron and hydrogen. So we get that. We get the iron released, red stuff, in solution, and we get the hydrogen to create the acidic condition. So that has a pH of around 2. Lead, same thing. We got, this is a lead ore, right? So we're taking lead ore, release the lead, release some hydrogen. And so what's the concentration of those metals in the aqueous phase going to be, high or low within that red stuff? Going to be really hot, right? Because we're going to have acid conditions. That's going to kind of inhibit, remember our adsorption-desorption reactions? When we have really low pH, lots of hydronium floating around, it goes to the particles, right? It gives it a positive charge, so it releases all those metals into solution. And here, in terms of precipitation reactions, it doesn't precipitate. Yes?
Please, can we say the EH and pH, are they opposite? Like if there is increase in pH, then there will be decrease in EH.
There is a relation, but it's not always that linear like that. So I don't want to say every time that you get, say, a decrease in pH, you're going to get a set amount of EH change. Okay, so it's not perfect. Okay, so pH 10, right? pH 2, what happens along that boundary? That's a pretty complicated scenario. I mean, we're taking one extreme and going to the other extreme. So we have really high stuff here. What's going to happen when it encounters?
Will it kind of neutralize?
Yeah, probably going to neutralize it. And so as we start changing the pH of this stuff, I mean, this is a big mass of water. So which way is the pH going to go? Probably going to go up. I mean, this might go down a little bit, but in reality it doesn't. There's so much of this stuff at pH 10, it raises the pH of this acid mine drainage. It just overwhelms it because of differences in volume of the liquids. Okay? So what's going to happen to the metals now that are in solution?
They mobilize.
What's that?
They mobilize.
Why would they be mobilized? They're mobilized here, right? You're thinking the right way, but the opposite direction. Okay, they're going to bind to the sediment, but we're going to have two things happen. Think of adsorption and think of precipitation, dissolution. What's in precipitation? What drives precipitation of metals here? So as pH goes up, remember, as pH goes up, we're likely to have more precipitation occur and less dissolution. So we are going to probably precipitate out some of your iron and other oxides and hydroxides and so forth along the boundary. In absorption, we're also going to do what? We're going to stick those metals to the clay particles or the iron oxides that are formed because of this precipitation, or manganese. We're going to stick it to the surfaces by absorption because absorption increases as pH goes up. Okay, so we have a couple of different processes forming it, all working together. This pH is going up, it's being neutralized, and as pH goes up, we're forming iron oxides and hydroxides, right? And those iron oxides and hydroxides are chemically reactive substances, so they're going to grab stuff out of the water, and they're actually going to absorb other metals that were in solution to the surface of those oxides and hydroxides by adsorption or exchange. Okay? So we've got a couple different things all going on here at the same time. And we can look at it in terms of these diagrams. So zinc is one of the things that's pretty high here because it's a zinc ore deposit, right? pH really low, it's even lower than that. We have really high concentrations of zinc within the water. And we can see that most of that's going to be in aqueous form, right? CN2+. But what happens now when it hits that more basic water? We drive this stuff this way. And what happens to the solubility of zinc? It comes all the way down, and what do we form? We're going to form zinc carbonates or zinc hydroxide, which are solids. So we're precipitating that stuff out, and then if we had iron in here too, we're going to stick that stuff, the iron oxides and hydroxides, through absorption. Okay. See how this works? And we can see here that, boy, the concentrations of the stuff that was in solution within that acid mine drainage stuff really is likely to decrease. Now, we would have to do some pretty detailed calculations to actually figure out the exact amount to quantify this. But conceptually, we can figure out what's probably going to happen here, right? We can just kind of look at those relationships and say, okay, well, our acid mine drainage is going to become buffered, and this is what we're going to have as a result of that. Make sense? Yeah? No? Okay.
Yeah, please, do you say increase in pH will increase precipitation?
Yes. So increase in pH is going to increase precipitation. Yeah. Now, I just put this in to show that it's not only true of zinc, but most of our toxic trace metals behave that way. Manganese kind of goes down because it's pH sensitive, right? It's redox sensitive. But the rest of these, as we get more acidic conditions, solubility goes up. And as we get less acidic conditions, more basic, solubility goes down. And if we have sulfur present, we can form these sulfides of low enough pH. All right, now in terms of adsorption, so precipitation, we precipitate this stuff out. And absorption, I threw this in because here's our sulfide. If it was buffered, this is what we would get. But since if it remains acidic, it's going to follow this line. Which line in this case would it actually follow? The acidity is going to get decreased, right? So we're going to follow this line. It's going to be buffered. And so we're actually going to have more absorption, a fair amount of absorption that takes place there. Yeah.
Do sulfides only form in acidic condition?
In reducing. Yeah. And it's really kind of a different process. That oxidation reductions kind of depends on each individual element that we're actually looking at. And so what's reducing for one element is not necessarily reducing for a different element. So we kind of have to keep that in mind. It's individually defined. And so we might have some sulfides being formed for one, say, manganese, where we're not getting it for iron, or vice versa. Okay, so let's go back to this diagram. That's kind of what's happening close to the mines here. But then that effluent and the pyrite and everything's being moved along, and we're going to use this example for a number of other discussions during the semester. But one of the concerns here is that as this stuff moves downstream, it actually impacts several villages or communities that are located along the river system. And this is a very mountainous terrain. And so every inch of flat ground is utilized for agriculture of some kind. And here's the real Pilcomayo out here in the background. You can see how mountainous this is. And then this is a little floodplain that's stuck down here in the valley. And you can see it's being used to grow a whole variety of vegetables. The community actually lives kind of further back away from the river system here. The agriculture's still a little primitive, but it's very effective. They come out with oxen and stuff, and they will create these very intricate irrigation systems that they reproduce every year. I don't know how they do it, but they are exact and precise, and they can essentially irrigate all of this stuff here during the dry season. This area has a very distinct wet and dry season. And so during the dry season, they can irrigate all of this terrain very effectively. And so, of course, one of the concerns is going to be what? Here's some of the irrigation canals comes out. Here's some onions. They got lettuce. They got potatoes. All kinds of potatoes. So like 100 different, literally 100 different kinds of potatoes that they grow. So what would you be concerned about here? Some of the little ones are out there watching us collect soil samples and things, but what would you be concerned about? Okay, could be affecting their water supply. It's a floodplain, so what else might be affecting it? Okay, soil's going to be what? Yeah, it could be contaminated. And what phase is it going to primarily be transported up into the soils? So let's take an example. We got during the wet season, water comes up, covers this entire surface, which it does very frequently. How is those contaminants going to be transported up on that surface? In aqueous form or solids? Kind of a trick question, because in part it'll be aqueous, but a large part of it, because of the pH, is going to be solids. So we know that, yeah, some of it's still going to remain in solution, no question. But the vast majority is going to be as particles or as coatings on individual grains. It's going to be transported in that particular phase, and then it's going to get deposited over this surface as sediments. And those soils are going to become contaminated with other contaminated particles. All right? Okay, so we can come out here and we can test that. But who cares? The soils get contaminated. What difference does it make?
Whoever eats that food probably cares.
Okay, why is that? Because the food, the vegetables might
take in some of those pressures.
Yeah, so that they might take up some of those metals, and some of those metals are really toxic, right? Especially lead. I mean, lead has some pretty significant neurological impacts on, especially on kids. And so one of the concerns would be, wait, what's the impact of lead on kids? And the pathway of exposure here is from the river to the soils to the vegetables to the people. And so then we're concerned about how much of that stuff gets into the vegetables, and then what is a typical load essentially for an individual based on how much potatoes and onions and carrots and stuff they eat, right? Okay. And the other thing with this is that these vegetables aren't just consumed within the community, they're actually taken to some of the larger cities like Sucre in this area and sold at the markets. So there's a lot of concern about that. Okay. Here's some corn. What's that stuff? What's it look like? Where else did we see it?
Stuff from the river?
Yeah, it's from the river. So this has been irrigated, and we can actually see the gray crap here, reduced environmental stuff, all right along the plants. And you would think they would be taking up quite a bit of metals and stuff right from irrigation from the river system. And this is some of the community. Here's what your concern is to make sure that they are remaining healthy. And so that's those guys up here. Now, all the way down here, we're about 500-600 kilometers downstream of Viamontes. Is another reason that potential contamination is an issue. It's actually the reason that we got involved with this back in the late 90s, early 2000s. And it's that this fish is called a sabalo, and it is the mainstay for various indigenous peoples along that part of the river system. They use it for, they trade, barter, it's essentially the basis of the economy, and they eat it. And so the concern is that in this case, it's the fish that are accumulating those metals and not by eating vegetables and stuff. So concern was, hey, how much of these guys pick it up? And then if they're picking it up, are the other people picking it up through consumption of fish? Okay, so there's a couple different exposure pathways that we have to be concerned. And spatially, they're separated by hundreds of kilometers. Okay, so let's go back. We essentially went along here, collected soil samples and whatnot from these villages up there. We also did some down there. And one of the things that we saw is that we can take samples from along the stream system all the way down to Viamontes, 500 and some kilometers downstream, and we can continue to see pyrite. So here, this is a photomicrograph, but these guys here, those are pyrite grains in the sediment. So we have pyrite, and this is the percentage. This is actually a graph produced by Karen Hudson Edwards, who's a geochemist in the UK. And she was able to document, the general decrease in sulfide minerals downstream. All right, we can look at this though. What's that stuff right there?
Oxidized pyrite.
Oxidized pyrite, oxidized sulfides, creating acid drainage from the oxidation of sulfides, which have been stored and preserved within those sediments along the channel. So during the high flow conditions, those pyrite grains get transported downstream. They get incorporated into the sediments that are deposited. And then we're here during the dry season. They're exposed to oxygen and create this acid drainage. And so we have this stuff right here, okay, which is acid. Out here, still more basic, right? So if we sample this, the water, and said how much is in the aqueous phase here, we're going to get one set of values, right? We're going to have really high concentrations. But if we came out here and sampled, we're going to get lower concentrations. Almost the same spot, different parts of the river, we're going to get two completely different things because we're getting all of this marginal stuff influenced by oxidation of the sulfides. It's creating acid drainage. This is more coming from the mines, which is more basic. And then as these two mingle, we're going to get these complex geochemical relationships going on, driven by changes in absorption and precipitation, that kind of stuff. So all this stuff's all commonly happening along these mine-contaminated river systems. All right, make sense? Okay, so let's move on here a little bit. Here's sampling the soils, different fields. And let's take a look at the soils themselves. So to understand this diagram, I know it's kind of a busy chart table, but Moan Dragon's real close to the mines. And then as we get further and further from the mines, we're looking at different communities. So Moan Dragon's closest to the mines, Sotomayor's a couple hundred kilometers downstream from the mines, and these are in between. So we're going further and further. We're going downstream this way, further and further for the mining operations. Number of samples that we collected. These are the lead, zinc, copper concentrations as you go across. And what we have here is the percentiles of the samples that were collected that exceed regional background concentrations. So what's regional background? What does that word mean?
Acceptable base levels of these contaminants.
you're right. It's a base level, but it's not, I wouldn't say acceptable. It's just what exists in the rocks and the sediments if they weren't contaminated by the mine. Okay? So in this case, the concentrations of those metals might be much higher than they would be in many other parts of the world. Why? Because this area is mineralized. There's lots of ore deposits already present there. So we might expect to have high concentrations of those metals in all of the rocks, or a lot of the rocks anyways. So we're looking at what we would expect based on areas of the river which are uncontaminated. That's our background level, our baseline information. And you can see here, Jesus, we're close to the mines. A large part of these soils are contaminated, or at least have higher than we would expect concentrations of lead, zinc, antimony, cadmium, and silver. Copper, not so much. So, in other words, these soils, yeah, they're pretty enriched in metals. Certainly much higher than what we would expect. And as we get further away, they're still contaminated, but just not as frequently. So some of the samples are, some of them are not. Interestingly, sotomayor here is silver. Still got a lot of silver in it way downstream. So they're losing a lot of silver when they're mining these things. In fact, some of these soils are almost economical. They had lost so much silver from the stream systems that were in the soil. Okay, so what do we know? This says the soils are pretty contaminated. So what's the next step? Did it take it up in the, the plant? Okay, so another complex diagram here. I just put it in here to give you an idea that we actually have the data. These are the guidelines that we use. So these are guidelines by, I believe it's World Health Organization, for commercially sold vegetables. So for lead, for example, there's different guidelines, but essentially you don't want to have ppms below about 0.25 or so, up to 1, somewhere in there. Zinc, you could have concentrations up to 50 ppm before we think that we might start getting a health effect. So that's what that guideline's saying. If we're above that, we're going to start having some health effects. But look, this is all corn, maize, carrots, onions, so forth. Look at the concentrations here of lead. With the exception of this guy for carrots, these two down here, leads are really low. And then look at this. There's like 1 for zinc. But all of this are below the guidelines for vegetables. So what's that saying?
They're not being affected that much.
Yeah, so the vegetables really aren't accumulating that much metal. So we know the soils are contaminated, they're heavily contaminated, but we see also that the vegetables, with a few exceptions of lettuce for lead and zinc, really aren't picking much up, okay? So what's that tell us about the bioavailability? Remember those terms? Bioavailability is how much of the total can be accumulated. Right, it's low. So we have a lot of metals there, but they're not bioavailable. Now, why not? What do we know about what's being transported downstream?
It's not in solution.
It's not in solution, it's in a particle. And we know that part of it is still associated with what was creating the acid mine drainage? Sulfides. Sulfides. So some of it has to still be associated with the sulfides all the way downstream. And then the other ones probably, as it gets absorbed, what's it getting absorbed onto? Onto the, could be, but probably a more important one. When those sulfides oxidize, right, and then it becomes buffered again, precipitates out iron and manganese coatings, right? So think of this: we take those sulfides and we oxidize them. We release the iron into solution. We're going to release zinc and so forth and acid. but then that gets buffered along the system, and it creates iron oxides and hydroxides. But iron oxides and hydroxides have a really high absorption capacity, right? So they start scavenging up all the metals and sticking it to that surface. So without really doing the detailed quantitative analysis here, conceptually we can say, one, some of this metal is likely to still exist within the pyrite grains and the sulfide grains and so forth. And then some of it is going to be reabsorbed. Some of that stuff that gets oxidized and released into the river system is going to be reabsorbed to particle surfaces. Things like iron oxides or hydroxides that are formed are probably going to scavenge a bunch of stuff out and stick it to the surface. So we would suspect, or might hypothesize, that the soils are going to have sulfides and then contaminated with various types of stuff stuck to the oxides. All right, so why is this important? Remember this diagram here where we get sequential extraction? And we said as we go down this list, things become less and less bioavailable. Look where the sulfide stuff are. They're way down here. They're almost non-bioavailable. Why is that? It's because the metals are actually stuck and locked within the crystalline structure of that sulfide. So even if it's ingested, we can't get it out. The only way we can get it out is if that sulfide is broken down, right? So that's where we're at there. But look at this. If we're sticking stuff onto iron and manganese oxides, primarily iron oxides in this case, it's still pretty, it's not very bioavailable. It's kind of moderately available here, right? So it's not like we're up here. We might have some up here, but a lot of it's going to be here. So in this case, we have a situation where because of the chemistry, because of the way it's transported and how it's moving, the soils are really contaminated, but most of it's not being accumulated within the vegetables, and therefore it poses a lower risk to those communities. But see how that worked? Okay, so was it no risk? No, because if we went back to this slide, we see some things like lettuce. There was actually, I thought carrot was in here. I mean, yeah, there's a carrot that's high. So there are some samples which might be contaminated with the metals, but overall it's lower than we might expect because it's not bioavailable. Now, actually, these values, there's some question because it's hard to analyze these dudes. So think of a lettuce, you know, how leafy it is and stuff, and you get soils and stuff on it. And what we were doing, we'd take this before we'd analyze it, we'd put it in a sonic water bath, we'd try to clean all of the particles and stuff off of it, and then we would process it, digest it, and analyze it. But we couldn't always get all that stuff off. So some of this might actually be particles on the surface of the leaves that we just couldn't get off. So it's hard for us to tell perfectly how much of that is contaminated sediment. All right, which brings us to another question. Where's that picture? Back. I thought I had it. It's here. You just can't see it very well. But I think it's that girl there. It's hard to tell. She's eating a carrot. Where'd she get that carrot? She just walked along and picked that carrot up, right? And then when she's eating it, what's she eating? The carrot plus sediment. So what was one of the things that we tried to help instigate here in terms of remediation, or help, I wouldn't say remediation, wash the veggies, or in the case of carrots, peel the veggies before you do it. And so there was David Preston, who was a sustainable kind of research scientist working in Bolivia for years and years. he started a program with the local nursing community to help educate the communities and say, hey, don't just go pick up the vegetables and eat them, but actually wash them or peel them or prepare them that way, and will kind of lower your potential ingestion of these things. Same with potatoes. Eat a lot of potatoes. And so another group working in the same area has come out and tried to look at accumulation of potatoes. They actually found higher accumulations in some of the potatoes than they did the vegetables we looked at. But they're saying, peel them and stuff as well. Okay. All right, last thing here is dealing with the fish. So if we look at the fish downstream, what we're going to find out is that most of that metals did not make it that far downstream to contaminate the sabala. And the reason for that is more geomorphic in nature. So we're going to be talking about that later on after the test than chemically. But it all comes back to the fact that most of the stuff was being transported into particulate form and not the aqueous form. So as a result, those contaminated particles got stored as sediments along this channel and weren't able to make it all the way downstream. So it wasn't a big issue there. All right, yep.
So like with just how big this area is, like you can do something like they did at the orchard, right? Where like they came and removed the sediments.
No, unfortunately, the area is just, the region is just so contaminated and you're such a large area that you can't really do that. Now, how do they attack it then? One of the approaches that people have taken here in the States is that if you have a town along that river, you could come in and try to clean up just around that town and clean it out. Doesn't work well here because the river floods that floodplain, and deposits contaminated stuff on a yearly basis. And so if you cleaned it up 1 year, 6 months later, it's going to be contaminated again. So it doesn't really work. You have to try to find out other alternatives to try to mitigate the effects of the contaminants.
And they're still mining like to this day?
Yes, but we'll try to get into this a little bit later on. But they've actually put tailings ponds upstream, and they've done a number of different things to try to curtail the amount of tailings and contaminants that are getting into the river system. So concentrations have actually decreased. And I think it's still a little bit debatable, but this other group that's working in the area, they are now arguing that most of the contaminants are not from the processing mills. It's actually from acid mine drainage coming out of the mines and some of the tailings piles. So it's certainly gotten better, and it's certainly the sources, the significance of the sources are changing a little bit different. So they're trying to make progress, but it's a pretty impoverished country and area. They don't have a lot of money to stick into doing this thing, and so it's hard to make progress. Yeah. Okay. Other questions? Starting to see how, even though we're not doing it quantitatively, we can start using our understanding of geochemistry, sediment relations, to make some conclusions about what's going to happen based on changes in pH and EH and those kinds of things. All right, I'm going to turn this off for a second.